Hello everyone, welcome back to this online class. Today we are going to look at the method of separation of variables as used in solving partial differential equations. In particular, we are going to solve the equation that is the two-dimensional Laplace equation that is given by second partial derivative of u with respect to x twice plus second partial derivative of u with respect to y twice is equals to 0. The domain for x is from 0 to 2. Similarly, the domain for the variable y is from 0 to 2. That's like a square. Our boundary conditions along, that is when x is equals to 0, the solution should be 0. When x is equals to 2, the solution is 0. When y is equals to 0, our solution is 0. And when y is equals to 2, our solution should be 80 sine pi x. So how do we go about this kind of equation using the method of separation of variables? So what we do, we are going to say that let u of xy, you see in our PDE, x and y are the independent variables. So u is a function of x and y. So let this be equal to x capital times y capital times y capital. And we are saying where x is a function of x, the small x, and y is a function of the small y. Now, because this is a solution of our given PDE, it must satisfy the PDE. So we must be able to find the partial derivatives of this u with respect to x and also with respect to y. So I can say therefore, second partial derivative of u with respect to x twice is equals to, you see we are differentiating a function of x, so anything that does not depend on x will be a constant. So in this case, y is a constant. So we differentiate x twice, keeping y constant. Similarly, second derivative of u with respect to y twice, in this case now x constant, differentiate y twice, y double prime. So then how will our equation look like? Now the PDE. Our PDE will now be, when we substitute, we are going to get x double prime times y, then plus x y double prime is equals to 0 on the right hand side. So this you can also write as, this implies that x double prime times y is equals to negative x times y double prime. Now what we have here is a separable ODE. This one is a separable ODE, and so we can be able to separate the variables by dividing both sides by x times y. So let me write, this is separable ODE. So how do we separate the variables? We divide through by x times y. So that upon division, we are going to get x double prime y over xy is equals to negative x y double prime over xy. And now you can simplify. You see the y will cancel. You can see x will cancel. So this simply means that x double prime over x is equals to negative y double prime over y. If you look at the left-hand side of this equation, you realize that we only have a function of x only. So the left-hand side is a function of x only. What about the right-hand side of this equation? I can only see functions of y only. So this is a function of y only. And we are saying the left-hand side is equals to the right-hand side. For that to be true, then each side must be equal to a constant k. So we can say that each side must be equal to a constant k. K here is a real constant. K is a real constant. A real constant. See, when you talk about real constant, we expect k to be either negative, positive, or 0. So that means there are three cases to consider. There's the case where k, I said, when you say k is a real constant, it means k belongs to the set of real numbers. So it can either be negative, it can be positive, or it can be 0, because the set of real numbers ranges from negative infinity to positive infinity. The 0 are there. And so k can be less than 0. That means it is negative. K can be 0, or k can be a number greater than 0, positive. So let's consider each case at a time. You write case 1. The case when k less than 0, k negative. So we are going to put k is equals to negative lambda squared, where lambda is a non-zero real number. Lambda is real and lambda not equal to 0. That's what we mean. So let's call this equation star. How will that equation star look like? This one. Call it star. So therefore, equation star will look like this. Equation star is now x double prime over x is equals to negative y double prime over y. And that is equals to negative lambda squared. From these equations, we can form a set of ODEs. The first one is x double prime over x is equals to negative lambda squared. Another one is negative y double prime, is a negative, over y is equals to negative lambda squared. So these are a set of ODEs, set of ODEs. These are second order ODEs. So let's call this equation 1, and this one, call it equation 2. We are going to solve those equations using the D operator method. So let's start by solving equation 1. Equation 1. If you cross multiply, that equation can now be written as x double prime plus lambda squared x is equals to 0. And now in terms of the D operator, this can be written as d squared operating on x plus lambda squared x is equals to 0. And you see this square x is common, so we can write this as d squared plus lambda squared operating on x to give us 0. Remember, in this case, the differential operator its derivative with respect to x. Take note of that. So we are saying, take note that what I'm calling d squared is the second derivative with respect to x. So now our auxiliary equation is, let me use another color, is d squared plus lambda squared is equals to 0. And now you can get the roots. Make d the subject, so there will be two roots, d1 and 2 is the square root of negative lambda squared. You see, every time you are squaring a negative, you are getting a square root of a negative number. Take note that you are going to get a complex number. So it will be plus or minus iota lambda, where I is the square root of negative 1. So then, how do we write the solution corresponding to x? So we are going to say, therefore, x is equals to, you see, the roots are real and distinct. You can write there, real and distinct. So then what do we do? Our solution here, general solution, will be C1 exponential lambda x. No, this was not real and distinct. These are complex conjugate roots. A correction. They are complex because of the I there. Those are complex conjugates. So when you have complex conjugate roots of that form, then your solution will now be C1 cos lambda x plus C2 sine lambda x. Let's see how to solve for y. So equation Roman 2. Equation Roman 2. That equation can be written as, remember, it is negative y double prime over y is equals to negative lambda squared. And you see the negative will cancel with this other negative, so that this equation can now be written as y double prime minus lambda squared y is equals to 0. Or in terms of the d operator, it will be d squared minus lambda squared operating on y to give us 0. What I'm calling d in this case now, the d squared is the second derivative with respect to y squared, or twice. So take note, there's the difference between the first d operator and the second d operator. Auxiliary equation. Auxiliary equation. Now equate the coefficient of y to 0. That will be our auxiliary equation. So we are saying that, let me use another color, that d squared minus lambda squared is equals to 0. So what are the roots of that equation? Make d the subject, there will be two roots. So that is square root of lambda squared, which is plus or minus lambda. Now here we have real and distinct roots. The roots are real and distinct. So how do we write our general solution when the roots are real and distinct? So therefore, you write y is equals to a constant C3 exponential lambda y plus another constant C4 exponential negative lambda y. So now we can be able to get the general solution of the given PDE. Hence, remember we said that u of xy is equals to the capital X times the capital Y. So we just multiply what is our capital X. We got here as C1 cos lambda X plus C2 sine lambda X times the other one we have C3 exponential lambda Y plus C4 exponential negative lambda Y. So that's what we have as our general solution, where C1, C2, C3, and C4 are arbitrary constants. Now, to find the particular solution, we need to apply the boundary conditions. Let's start by applying the first boundary condition along x. So you can write apply the boundary conditions. The first condition is when x is 0, u0, y is equals to 0. So what happens? That we substitute x is equals to 0 so that you get u is equals to 0 in this general solution. So let's substitute, we see what you're going to get. So we're going to get 0 is equals to, when x is 0, remember sine 0 is 0 and cosine of 0 is 1. So in the first bracket, I only have C1. The second bracket, we just return it because there's no x there. So C3 exponential lambda y plus C4 exponential negative lambda y. Now, we need a non-trivial solution. If you need a non-trivial solution, then it means this cannot be 0. So we only remain with C1 being equal to 0. So you can write for a non-trivial solution, it is only C1 that can be 0, but not the other one. So therefore, how will our equation become? Look at the general solution. It will now be u of xy is equals to, remember C1 is 0, so we only remain with C2 sine lambda x times C3 exponential lambda y plus C4 exponential negative lambda y. And this you can simplify. If I take the C2 inside, let it multiply C3. We are taking C2 times C3. Again, the same C2 times C4. So we are going to say let A be equal to C2 times C3 and B be equal to C2 times C4. Because I told you, when you multiply any two arbitrary constants, you need to get an arbitrary constant. So that this solution, the reduced general solution, can now be written as sine lambda x times A exponential lambda y plus B exponential negative lambda y. That is the reduced general solution. Now, we also have another boundary condition. Let's apply the boundary condition at x is equals to 2. 2y, again, this is 0. What does it mean? That when you substitute x is equals to 2 here, you need to get u is equals to 0. So therefore, this again will give us 0 is equals to, remember x is 2, so this will be sine 2 lambda a times exponential lambda y plus b times exponential negative lambda y. Again, we need a non-trivial solution. So if you want a non-trivial solution, then this cannot be 0. So we only remain with sine of 2 lambda, which can be equal to 0. So remember, for a non-trivial solution, it is only sine of 2 lambda that can be equal to 0. So I need to find lambda. So you need to take sine inverse on both sides. This means that 2 lambda is equals to sine inverse of 0. And you know there are so many angles whose sine is 0. So therefore, 2 lambda, there will be so many of these lambdas because there are so many angles whose sine is 0. So the sine inverse of 0 will give us n pi. Pi is 180 degrees. N is a natural number. So or lambda n is equals to n pi over 2, where n is a natural number. That is from 1, 2, 3, etc. Somebody might ask, why are we not starting from n is equals to 0? You see, when we start from n is equals to 0, that will reduce us to case 2, where k was equals to 0. Or that means lambda will be equal to 0. And we started by saying that lambda cannot be equal to 0. So that's very important. Now, let's substitute that into our solutions. And I told you, you see, what we are calling lambda n, these ones are called eigenvalues. These are eigenvalues. Now we need to find the corresponding eigenfunctions. Those eigenfunctions are given by u subscript n of xy is equals to, just from here, look at this solution. Where there is lambda, we substitute lambda subscript n. So that will be sine lambda n x times a. Even these constants are so many, exponential lambda n y plus b subscript n exponential negative lambda n y. And so this is equals to sine of lambda n is n pi over 2. Here we have x, a subscript n exponential n pi over 2y plus b subscript n exponential negative n pi over 2y. That's what we have. Now, for us to get our solution for the PDE, that is, the solution is u of xy. We use the principle of superposition. So, using the principle of superposition, our solution u of xy is equal to the sum from n is equals to 1 to infinity of u sub n of x, y. When you sum all the eigenfunctions, you get your solution u of x, y. And so this is the same as the sum from n is equals to 1 to infinity sine n pi over 2x times a subscript n exponential n pi over 2y plus b subscript n exponential negative n pi over 2y. So that's what we have. Now, we still have two boundary conditions to apply. That is at y is equals to 0 and at y is equals to 2. Let's apply this. U x when y is 0 should give us 0. We are now applying it here. Look at the one I have ticked. So that means I'm going to put y 0 and u is equals to 0. What are we going to get? So we're going to get 0 is equals to the sum from n is equals to 1 to infinity sine n pi over 2x. You see, when you put y 0, we are going to get exponential 0, which is 1. So here we'll only have an plus bn. Those are constants. This is half-range Fourier sine series of 0, where the Fourier coefficient is an plus bn. So clearly, remember, we are saying this is half-range Fourier sine series of our function is less 0. So how do you get the Fourier coefficient? So an plus bn, that's the whole constant, is equals to, remember our interval was from 0 to 2. So it is 2 over 2, integrate from 0 to 2, 0 times sine n pi over 2x dx. When you integrate 0 and you have the limits of integration, the result should be equal to 0. So therefore, you see, we are saying an plus bn is 0, an plus bn, that is 0, or we can get bn is equals to negative a subscript n. That's what we are getting. So this is very important. Now let's replace where we have b subscript n, we are going to replace that by a subscript n here in this equation. So therefore, you can just say therefore, u of xy is equals to, remember, here now instead of bn, it is negative of a subscript n. So you see a subscript n is common. I'm going to factor that out. So this will now give us the sum from n is equals to 1 to infinity of a subscript n sine n pi over 2x, and the other one is exponential n pi over 2y minus exponential negative n pi over 2y. That's what we have. And finally, we have the last boundary condition at y is equals to 2. So we now apply u of x when y is 2. What was the result? It was 80. Let me just check up there. The last boundary condition. That was equals to 80 sine pi x. 80 sine of pi x. So I'll go down so that I can write 80 sine, that should be sine, 80 sine pi x. What does it mean? That when you put y is equals to 2 in this equation, you need to get u is equals to 80 sine pi x. So we are going to say 80 sine pi x is equals to, remember now y is equals to 2. So this is the sum from n is equals to 1 to infinity, a subscript n sine n pi over 2x. And here we have exponential. That should now be n pi, because y is equals to 2, then minus exponential negative n pi, because y is equals to 2. And you see, this thing can also be written as, if I say let, I can just say let a subscript n be equal to, let's say, the small b, the small bn, or simply twice. Let it be bn over 2, that one. So that I can now write this as, this can now be written as equal to the sum from n is equals to 1 to infinity. Now we'll talk of bn. Remember, it is bn over 2. I want to take the 2 here, so that is exponential of that divided by 2. So here we'll have sine of n pi over 2x times exponential n pi minus exponential negative n pi, and you divide by 2. I've taken the 2 here. Now, what do you think is this? Whatever we have in the bracket, this one here, that bracket is the same as hyperbolic sine of n pi. So this is the same as sine hyperbolic of n pi. So this you can as well write as the sum from n is equals to 1 to infinity bn sine n pi over 2x times hyperbolic sine of n pi. On the left hand side, what do we have? We have 80 sine pi x. That's what we have. Therefore, how do we find, again, you see this is a Fourier series. This is half-range Fourier sine series. So you can comment on this one again. Comment on this series. You write this is half-range Fourier sine series. Half-range. Let me use Fs to mean Fourier sine series. Fourier sine series of the function 80 sine pi x in the interval x belonging to the interval 0 to 2. That was the domain from 0 to 2. So how do you find the coefficient? Remember this constant. Look at this. B subscript n, you will combine it with sine hyperbolic of n pi. That is a constant. So therefore, there are two ways you can do this. Two ways. The first way, method 1, I am going to expand the right-hand side. So we are saying that 80 sine pi x, when you expand the right-hand side, when you start with n is equals to 1, we are going to get b1. b1, remember n is 1, so that will give us sine pi over 2 x times sine hyperbolic of pi. That is when n is 1. When n is 2, we'll talk of b2 sine pi x times sine hyperbolic of 2 pi, plus when n is 3, we'll talk of b3 then sine 3 pi over 2x sine hyperbolic of 3 pi plus so many other terms up to infinity. Then what you do, you compare the corresponding coefficients. I need the coefficient of sine pi x on the right-hand side. So sine pi x, it is this one. Let me bracket that properly. Sine pi x is this. So what is the coefficient on the right-hand side? It is b2 times sine hyperbolic of 2 pi. The rest are zeros except at b2. So we are saying when we compare the coefficient of sine pi x, we get that 80, let's write coefficient of sine pi x. What will it give us? That 80 is equals to b2 times sine hyperbolic of 2 pi. So from here, I can make b2 the subject. So from here, we are getting b2 is equals to 80 over sine hyperbolic of 2 pi. What about the other b's? You realize that b1 is equals to 0, b3 is equals to 0, etc. So b1 is equals to 0, b3 is equals to b4, which is equals to so many other b's, and the result is 0. There is only b2 that is equals to 80 over hyperbolic sine of 2 pi, but the remaining are zeros. So you can as well say that the b subscript n, you can just say that therefore b subscript n, that Fourier coefficient, is given by, it is 80 over sine hyperbolic of 2 pi, or it is 0. So when is it 80 over sine hyperbolic of 2 pi? That is if n is equals to 2. And it is 0 otherwise, for any other value of n. That means when n is not equal to 2. That's how to find the Fourier coefficient using the first method. Another method is when you use the integration. So you see, I told you this is a half-range Fourier sine series expansion of 80 sine pi x over the interval 0 to 2, x0 to 2. So method 2 is this one. Let me write it here. Method 2. Now, the whole of that Fourier coefficient, look at our series. We are going to take Bn times hyperbolic sine of n pi, because that's the constant. That is the coefficient we need to find. So you are going to write the Bn times hyperbolic sine of n pi is equals to 2 over 2 times the integral from 0 to 2, our domain is from 0 to 2, of 80 sine pi x, 80 sine pi x, times the other function. What was it? Look at our series. Sine n pi over 2x. So the other one is sine n pi over 2x. N pi over 2x dx. And you see 2 over 2 is 1, so I don't even need to write this. 2 over 2 is 1. This can be written as 80 outside, the integral from 0 to 2 of sine pi x times sine n pi over 2x dx. Look at this integral. This integral is the same as, when you integrate this, you're going to get, it is 1 if n is equals to 2, and it is 0 otherwise, when n is not equal to 2. So it has two parts depending on the value of n. So therefore we expect our result here to be 80 times this one. And remember, on the left hand side we had Bn times sine hyperbolic of n pi is equals to that. So you can now make Bn the subject. Therefore, from here, you get that Bn is equals to 80 over sine n pi. That was sine hyperbolic. Let me correct it here before we propagate the error. Sine hyperbolic of n pi times 1 or 0. And we said it is 1 if n is equals to 2, and it is 0 otherwise. So times 1 if n is equals to 2, and 0 if n not equal to 2. You could also take the whole of this inside so that you get what we got in method 1. So when you multiply, you're going to get what? So this will still give you this. It will give you 80 over sine hyperbolic of n pi or 0. So this is if n is equals to 2, if n is equals to 2, this other one if n is not equal to 2. You see, we have found the same thing as in method 1. The method 1 seems to be easier. We're just comparing the coefficients. Now, with that Bn, only B2 is valid, the rest are zeros. So we come back here, look at our solution before we applied the other boundary condition. This was our solution that we are dealing with. So let me bracket it. This is the one that we were dealing with. So here it is only B2 that exists, the rest are zeros. So even the summation will not even be there because it's like we are having 0, which corresponds to B1, plus that corresponding to B2, plus other zeros. So you can just say, therefore, let's call this equation star star so that we can refer to it easily. So that equation, was it that really? So that equation, of course, this one, I want the one with the Bn. The Bn, here you can write this as Bn, then this one is over 2. Remember what we said? That where we have a n, it is supposed to be equal to Bn over 2. So that is Bn. Let me write this up. This one. Just a minute. So you write this is Bn over 2. Instead of a n, we'll talk of Bn. Then the 2. So when we divide by 2, so what will be this one? This is the same as sine hyperbolic of n pi over 2y. That's what we have. Equation star star can be written as that one now. So let me write it here again. So equation star star, you can write this equation star star can be written as u of xy is equals to the sum from n is equals to 1 to infinity. We are replacing, remember we said where there is a subscript n, that should be b a subscript n over 2. That's what we are doing. So it is b subscript n sine n pi over 2x times exponential n pi over 2y minus exponential n pi over 2y. This is negative now. That should be negative. Let me write it a better way. Negative, then you divide by 2. That's what we have. So what is that? It is hyperbolic sine of n pi over 2 times y. So this you can as well write as the sum from n is equals to 1 to infinity Bn sine n pi over 2x times hyperbolic sine of n pi over 2y. But you see, we know the value of Bn, that when n is 2, it is supposed to be 80 over sine hyperbolic of n pi. So when I expand this one, it's the same as when n is 1, we talk of B1 sine n is 1, so that will be pi over 2x. This is hyperbolic sine of pi over 2y. When n is 2, we talk of B2 sine pi x, then hyperbolic sine of pi y, plus when n is 3, that will be 3 sine 3 pi over 2 x, then sine hyperbolic sine of 3 pi over 2 y, plus so many other terms up to infinity. But we said b1 is 0, so I expect all of this to vanish. This is 0 because b1 is 0. b3 is 0, and even the other terms which remain, those will be zeros, except b2. What did we say b2 is? Check. When n is 2, you find that b2, when n is 2, b2 should be 80 over sine hyperbolic of 2 pi. So where there's b2, we put that. So what we'll have finally, it will now reduce to 80 over sine hyperbolic of 2 pi, that's b2, times sine pi x times sine hyperbolic of pi y. And on the left hand side, we have u of xt. So you can just say that, or not u of xt, it is u of x, y. So this one is our solution, our particular solution of the given PDE. So this is the particular solution. See, it is a function of x and y. Now this is case 1. Case 2 will give us a trivial solution. Case 2 is the case where k is equals to 0. I wanted to show that in case 2, we are going to get a trivial solution. So the answer here is that u of xy will be equal to 0. You can show that, of course, we have done in so many other examples. So in case 3, that is when k is positive, k greater than 0. You are going to put k is equals to now positive lambda squared, where lambda is a non-negative real number. Where lambda is a non-negative real number. Lambda not equal to 0. Remember, in case 3, we are putting k is positive lambda squared, not negative, just like in case 1. So again, the answer here, you're going to check to verify that even in this case, your answer u of xy will be equal to 0. So you realize that the solution in the other two cases is trivial. This is a trivial solution. Similarly, this other one is a trivial solution. So the only solution that is of interest to us is the one that we got in case 1. U of xy is equals to 80 over sine hyperbolic sine of 2 pi times sine pi x times hyperbolic sine of pi y. So even in the exam scenario, you only need to work with case 1. The other cases, don't waste your time working with them. So thank you all for watching this video. Please subscribe to my YouTube channel. That is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When we meet next time, we will look at other problems in the method of separation of variables. Bye-bye.